To understand the matrix of a linear transformation between two vector spaces, first we need the notion of a coordinate isomorphism. So let's start with that coordinate isomorphism. Right, let's let V be a vector space with, let's say the dimension of V is n. And let's let B, given by B1 through Bn, let's let this be a fixed basis of V. Okay, now let's define the coordinate isomorphism, which is a map from V to Rn, given as follows. So we say CB of, and then we'll take linear combinations like, whoops, A1, B1 plus A2, B2 plus et cetera, plus AN, BN. This is equal to A1, E1 plus et cetera, plus AN, EN, which we really just write as A1 through AN. And what this is, right? What is this doing? Well, we have a basis of V given by B1 through Bn, and then we have a standard basis for Rn given by E1 through En. And basically this coordinate isomorphism is what it's doing is saying, okay, what would the vector look like, for some given, V, which is equal to A1, B1 plus et cetera, plus AN, BN. What would the matrix look like in Rn? Or excuse me, what would the vector look like in Rn, right? So this coordinate isomorphism is just mapping, and it's swapping out the basis elements here, and then we're looking at the vector that we get in Rn, and we use this to our advantage because when we want to define, if we want some matrix that represents a transformation between two arbitrary vector spaces, well, we think about coefficients of matrices being in Rn or Rm, right? We think about coefficients being real numbers. And so to find a matrix M representing such a transformation, we first need this coordinate isomorphism so that we know what we're talking about in Euclidean space still. So let's look at an example. Let's say V is given by the space P2, the vector space, and we want to find. So let's say we're looking at the vector space P2, and then let's also say we're looking at an element of P2, V, given by negative x squared minus 2x plus 4, and we want to find the coordinate. So I should have said here, I think I got a little bit ahead of myself. This value here, this is called the coordinate vector of V, right, where V is equal to this linear combination with respect to the basis B. Okay, so that's a definition that I kind of skipped over there. We've talked about this in the context of Rn to Rn, but I need to redefine everything in a more general setting, right? So what we want to do now is we want to calculate the coordinate vector for this element of P2 in 3 different bases. And so find CBV, where first we're going to be looking at the basis B is equal to 1xx squared. Next, we're going to be looking at B is the basis x squared x1. And then thirdly, we'll be looking at the coordinate vector of V when the basis is x plus x squared, x, and 4. Okay, so let's do that. Let's start with 1, right? And this was the basis b given by 1x squared. So what do we need to find, right? Well, we're looking at the vector v, which is given by negative x squared minus 2x plus 4. Then the coordinate vector v is, you apply the isomorphism to the element negative x squared minus 2x plus 4, which this is equal to a1 times 1 plus a2 times x plus a3 times x squared, because those are our basis elements here, right? And so this is going to be then the vector a1, a2, a3, and you can see what we have is that a1, well, what's the coefficient of the constant term? That's 4. So we get 4. What's the coefficient of the x term? That's -2, so we get -2. And then what's the coefficient of the, of the x squared term? Well, that's -1. And so this is the coordinate vector CBV under the first basis here, where this is our given basis. Let's do it for the next basis, right? For the next one, we had b was given by x squared x1, which is just a permutation of the basis elements, right? The elements themselves are the same, they're just permuted, and so they're in a different order. Well, CBV is equal to CB of negative x squared minus 2x, minus 2x plus 4, and this is equal to a1 of x squared plus a2 of x plus a3 of 1, right? The order matters here. I've written this combination in the appropriate order because the vector will look different, right? This is going to be a1, a2, a3, which is, here we can see -1, -2, 4. And this is CBV for the second basis that we're considering, the second basis of P2. And you'll notice as vectors, the answers are different, right? Those are not equivalent vectors, although it's representing the same vector just with respect to two different bases. Let's look at the third one. For the third one, we have b is x plus x squared, x and 4, like this, right? So what do we need to do? Well, we need to look at CB of v, which is CB of negative x squared minus 2x plus 4, which is going to be a1 times x plus x squared plus a2 times x plus a3 times 4, right? Because now these are our basis elements that we're looking at. Okay, so what does this mean, right? Well, this means we need to set up the equality negative x squared minus 2x plus 4 equals a1 x plus x squared plus a2 times x plus a3 times 4, and we need to solve for a1, a2, a3. That will give us the coordinate vector, right? Because this is going to be equal to sum a1, a2, a3. Well, this gives us a1x plus a1x squared plus a2x plus 4a3, which gives us a1x squared plus a1 plus a2x plus 4a3. We equate coefficients. So we have -1 is equal to a1. For the second piece, we have -2 is equal to a1 plus a2. Wait, what? Yeah, -2 is equal to a1 plus a2. And then for the third, we have that 4 is equal to 4a3, which implies that, well, let's just write 4 is equal to 4a3. So we have that a1 is equal to -1, a2 is going to be equal to -1, and then a3 is equal to 1. And so for the third basis, CBV is equal to the vector -1, -1, 1. Again, very different, but you will notice that all three of these vectors that we've calculated for the three different examples, that's all describing the same element, just with respect to different bases, right? And so that's important to note. And really what you can think about happening is that's shifting the space around the vector, right? And so your units of length are different, but it's the same vector. Cool. Because of a coordinate transformation, or because it's an isomorphism, this means CB inverse from Rn to V is also an isomorphism, right? Is an isomorphism given by CB inverse of A1 through AN. This is equal to A1 B1 plus A2 B2 plus et cetera, plus AN BN for all A1 through AN contained in Rn, right? So that's important to note. Remember, we've proven, I think yesterday, actually, we proved that the inverse of an isomorphism is also an isomorphism, right? And so we've proven that already. And what I'm doing here is this theorem states that the inverse is given precisely by this. It doesn't take much proof because you compose in either direction and you get the identity on either Rn or the identity on V, depending on which direction you compose in. So we need to know of the existence of the inverse and that it's an isomorphism here when we want to be able to compute the matrix that represents a given transformation. So let's set the stage here. Let's let V be, well, V sub n, this is going to be an n-dimensional vector space with basis B, which is B1 through Bn. Let's let Wn be an be an m-dimensional vector space with basis B2. And sorry, I should have said B1 here. You could denote these as BV and BW if that helps keep track of things better. Now, the next theorem shows us how we can compute the transformation matrix, or how we can compute the matrix that represents a given linear transformation. So theorem. We have, well, maybe before I state the theorem, let's state a few more prerequisites here. So we're going to be considering T from V to W. This is going to be a linear transformation. Okay. We know that CB1 is going to be the coordinate isomorphism of V from V to Rn, and CB2 is going to be the coordinate isomorphism from W to Rm, right? So here's kind of all of our prerequisite stuff. We have V, W, a map between them, a linear transformation from V to W, and then their coordinate isomorphisms, respectively denoted CB1 and CB2. And so here's the theorem. The unique matrix M B sub 2 B sub 1 of T representing T from V to W is given by And I should say this is with respect to the bases B1 and B2, right? But that's kind of apparent in how I'm denoting this. This is defined to be the matrix that consists of column vectors CB2 of TB1, et cetera, through CB2 TBN. So this is an N by M matrix, in column, M rows, right? And here, what are we doing, right? For each column, so let's write out what we have here, right? We have T going from V to W, and then we also have these coordinate transformations, Rn to Rm here. And really, this is where the matrix is going to live. M, B2, B1 of T, right? Because a matrix is still a function from Rn to Rm. Here we have the map T. Here we have CB1, and here we have CB2. And basically what we're saying is that M B2 B1 of T is equal to, well, first you would do CB1 inverse and then T and then CB2. This is exactly what you would get, right? If you look at the commutativity of this diagram, meaning if you start here, like it's intrinsic of what path you take, you get the same thing, right? And so we're defining this map here to be, well, you go CB inverse first, and then T, and then CB2. And I have this flipped, right? Because you always work. So like CB1 inverse, and then T, and then CB2. And what is CB1 inverse, right? Well, CB1 inverse is going to be, this is going to be equal to CB2 of T. And then what is CB1 inverse, right? Well, that's just your basis elements, B1. If you do that on the standard basis in Rn, right? The standard basis in Rn is E1 through En. The inverse image, right? Or the image of CB1 inverse of, if you take just E1, well, then the image is going to just be B1, right? And so this would be like Bi, for I goes from 1 to N. And then this is exactly what we have here. This is exactly how we're defining the matrix representing a linear transformation. And so we have to understand these coordinate transformations here, these coordinate isomorphisms, in order to calculate the matrix representing a given transformation. So let's do an example, because this could seem kind of abstract and confusing. So let's look at a transformation T from P3 to R4, given by T of ax cubed plus bx squared plus cx plus d is equal to a plus b, b minus c, c plus d, and d plus a. And let's find, well, and let's state two bases here, where b sub 1 is going to be the basis x cubed, x squared, x1. And what basis are we going to use for B2 or for R4? We're going to use the basis 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, negative 1, 0, and 0, 0, 0, 1. Cool. And so we want to find M, B2, B1, T. So we want to find the matrix that represents this transformation from polynomials of degree at most 3 to 4-dimensional Euclidean space. Cool. Well, what do we need to do, right? Well, we know that MB2 B1 of T is going to be equal to the matrix composed of column vectors CB2 T x cubed, right? Because we're looking at basis elements of B1. So that's B1, B2, B3, B4, right? And so x cubed, we need CB2 T x squared, CB2 T of x, and then, so sorry here for the fourth column, excuse me, but CB2 T of 1. So to compute this matrix, we need to compute T of x cubed, T of x squared, T of x, and then T of 1. Well, what is T of x cubed? T of x cubed is the element when A, this corresponds to A equals 1, and then B equals C equals D equals 0, right? That's how you get x cubed from this, for an element of P3, which means when we plug those values into the vector, we're going to get 1, 0, 0, 1. 1, 0, 0, 1, right? So that's the image of x3 under this transformation based on how it's defined. We do the same thing for x squared. That means b is equal to 1, everything else is equal to 0. So that's going to be 0, 1, 0, 0. And then for x, that means c is equal to 1, everything else is equal to 0. So we're going to get 0, negative 1, 1, 0. 0, negative 1, 1, 0. And then for 1, that means d is equal to 1, everything else is equal to 0. So 0, 0, 1, 1. Right? Which means now we understand how the basis of P3 is transformed under T, but now we need to look at the coordinate vectors for the images of those, right? So MB2 B1 of T is then equal to CB2 of T of x3, which was 1, 0, 0, 1, and then CB2 of, and the rest of it, right? We had 1, 1, 0, 0, CB2 of 0, negative 1, 1, 0, and then CB2 of 0, 0, 1, 1. So now, right, where again, these are column vectors. Now let's compute these column vectors. So we need CB2 of 1, 0, 0, 1. How do we compute CB2 of 1, 0, 0, 1? Well, this is equal to, well, we have to understand what 1, 0, 0, 1 is in terms of the basis for, or the basis elements of B2, right? That's why it's CB2. So let's take these elements here, right? And this is going to be equal to like A1, A2, A3, A4, where 1, 0, 0, 1 is equal to A1, you know, and then the basis vectors of B2. So I'll just write them down here. You can see what they all are. The first one is 1, 0, 1, 0. Plus, A2, and then the second element of B2 is 0, 1, 0, 0, and then plus A3, the third basis element of B2 is 0, 0, negative 1, 0, plus A4, which is 0, 0, 0, 1. Now, if you look at this, we get the following system, right? From the first component of this equality, we get that A1 is equal to 1, A2 is then equal to 0, A1 minus A3 is equal to 0, and A4 is equal to 1, right? Again, this system came from looking at, you know, you look at this equality, you look at the equality component wise. So if you read off the first component, you have 1 equals A1. If you read off the second component, you have 0 equals A2, right? Et cetera, et cetera. And so you can see here, this yields rather quickly that A1 equals 1, A2 equals 0, A3 equals 1, and A4 equals 1, which implies that CB2 of what we were calculating, 1, 0, 0, 1 is equal to, and what we got, 1, 0, 1, 1. So when we come back to, when we have M, B2, B1 here, we know the first column will be the image, or CB2 of 1, 0, 0, 1, which was 1, 0, 1, 1. So that's the first column. And you go through an identical process, right? So what about, well, here I claim that you get the following things here. And you can verify here. And that would be good for you to do so you can go through an example of this. C of B2 of T of X squared, which is equal to C of B2 of, and this was going to be the second column, right? So 1, 1, 0, 0. You go through the same process, and I claim you get 1, 1, 1, 0. C of B2 of T of X, which is C sub B2 of 0, negative 1, 1, 0. I claim that you get 0, negative 1, negative 1, 0. And then lastly, for C B2 T of 1, which we calculated to be CB2 of 0, 0, 1, 1, I claim that what you get is 0, 0, negative 1, 1. Putting all of this together, right? 1, 1, 1, 0, and then 0, negative 1, negative 1, 0, and 0, 0, negative 1, 1. And so I want you to verify that my calculations are not incorrect. And that means this matrix here. So let's write this out in entirety here. So we had the transformation T from P3 to R4 given by T of AX cubed plus BX squared plus CX plus D is given by, where'd it go? It was A plus B, B minus C, C plus D, D plus A. And the matrix, with respect to the given bases, describing this transformation is what we got. So 1, 0, 1, 1, 1, 1, 1, 0, 0, negative 1, negative 1, 0, and 0, 0, negative 1, 1. So this is how you find transformations, or how you find matrices that represent a given transformation between two vector spaces. And you can see it was a little more complicated here when one of them was not just straight up Euclidean space, right? Because you have different basis elements, they behave differently depending on the transformation, et cetera, right? So I think this about wraps up new material for the course. So if you survived this far, congratulations. This is not easy material. Matrix theory is a very tough subject, and really, as hard as it is to believe, this just kind of scratches the surface of a lot of really interesting theory, especially spectral theory. There's so much going on with eigenvalues and eigenvectors. It's very, very cool stuff. Same here. You may notice there's a lot, this hints at a lot more abstract notions that we call abstract algebra and that we study. So I hope you've enjoyed the course material. I hope it's helped improve your understanding, but maybe also your appreciation for mathematics and algebra as a subset of mathematics. This is not the last you'll hear from me, though, of course. Tomorrow's video will be a final review. Basically, I'll pick some problems from the practice finals that I've posted on the Canvas page. I'll go through, not very many of those have a solution set. So I think I'll go through and provide a solution set for those, maybe walking through it in detail. which will serve as practice for the final. But otherwise, I've had a great time instructing all of you, and best of luck during the final.